Okay, so exponential regression. Just like linear and quadratic regression, this is going to be something we type in the calculator. Choose exponential regression, get an equation for it, and use that equation. But first, I want to talk about what an exponential regression or exponential function looks like in terms of a table. Like, how can you tell kind of an exponential from the table? Well, the first thing is exponential growth will look something kind of like this, where you start off really, really small, like 2/3, and then 2, and then 6. Then you're getting bigger all of a sudden, right? 18, and then, whoa, 54, like came out of nowhere. Like it grows slow, but then it grows really fast. And we saw that before when we did exponential functions. But the pattern we're looking for is a pattern of multiplication. How do we get from one term to the next? Well, instead of adding something or subtracting something, we're actually multiplying by a value. So you can see all of these from one term to the next are multiplying by 3. And so that is the sign of an exponential function. Is the pattern a multiplication pattern? So we call that a common ratio, by the way. This 3, we call that the common ratio. We say the common ratio of this is 3 to note that's what the value is going up by every time. Remember linear functions, we did that. We found the first differences were constant. For quadratics, the second differences are constant, and so on. Well, we're still going to do that a little bit here. So let's analyze, let's determine if this is exponential, and if it's not, let's see if we can tell what type of function it still is. So if we look at the differences here, going up 1, this one's going up 2, this one's going up 3, and this one's going up 4. So it doesn't look like there's a pattern of multiplication, because I'm not really multiplying 2 by, 2 times 1/2 gets me to 3, but 3 times 1/2 does not get me to 5. Or not 1/2, but like 1 1/2. But if you look at the adding differences, plus 1, 1 to 2 is going up 1, 2 to 3 is going up 1, and 3 to 4 is going up 1. This is actually a quadratic. Let's go ahead and label it. It's not exponential, but that's actually quadratic. Let's look at the next one. 16 to 24 going up 8. 24 to 36 going up 12. 36 to 54 going up 18, and then 54 to 81. 31 minus 4, 27. 27. And if you look at those differences, that's a difference of 4, that's a difference of 6, that's a difference of 9. So you see, first difference is not the same, second difference is not the same, so it's not linear, it's not quadratic, but notice the ratio remains the same. From one term to the next, what's actually happening is you're increasing by 1.5, by 1.5. 4 times 1.5 makes 6. 6 times 1.5 makes 9. And that's true on these upper levels as well. 8 times 1.5 is 12. 12 times 1.5 is 18. 18 times 1.5 is 27. And even all the way up here, all of these are still the pattern that you might notice is that they're all being multiplied by 1.5. 16 times 1.5 gets you 24. 24 times 1.5 makes 36, etc. So the fact that, these values didn't change, but the ratio stayed the same, kind of gave me a hint that it was the exponential. This is exponential, by the way, because we're multiplying by a common value. Now, how do you know it's 1.5? I know it's 1.5 because I'm really good with numbers, but how do you know it's 1.5? Well, if what you're doing is taking something, 16, and multiplying it by some number to get 24, and then again, 24, multiplying it by some number to get 36, well, do it the opposite way. 16 times something equals 24. Well, then, if you want to know what that something is, well, then divide this by 16, right? That something, 24 divided by 16, is 1.5. So you can actually work backwards. If you go backwards and you divide, you can actually get that x value or that ratio value. So that's always a good trick. And you can do that with any of these. If you take 36 and divide by 24, you'll get 1.5. And that'll work on any of these 81 divided by 54, still going to get you 1.5. So that's a little trick that you can use to find that common difference if you can't see it off the top of your head. Okay, I broke it. Oh gosh, I broke it. I broke it. I actually broke it. I don't know what I did. Okay, hold on. We're gonna turn autosave off. Yeah, and I don't care about this. Let me just go back and find my exponential. Where'd it go? There it is. All right. We were here. So if we want to look at these, let's look at the differences. Now this one, based on the fact that this is 2.6 repeating, that's not going to happen. If I'm adding another number, it's going to be another repeating decimal. So it's clearly not a pattern of adding. So 2.6 times something gets me to 4. 4 times something gets me to 6. 6 times something gets me to 9. And 9 times something gets me to 13.5. If I want to figure that out, well, let me just take one of these and go backwards. So let's take the 9 divided by 6, for example. 9 divided by 6 is 1.5, I think, right? So 9 divided by 6, 1.5. So that's good. Let's just check that the other ones are still the same thing, right? Let's check 6 divided by 4. 6 divided by 4 is also 1.5, so that's good. I'm just going to make sure that all these match up. What about 4? Well, that's like a weird decimal. What about this one, right? 13.5 divided by 9. That's also 1.5. So I'm going to take it on good faith that 4 divided by 2.66666 repeating is 1.5, and it is. So that's something you can do if you want to check. All of those were 1.5, so that tells me, that my common ratio here is 1.5. So it is exponential, by the way. All right, and what about this one? Negative 3 to 2, 2 to 7, 7 to 12, 12 to 17. I can see that these are all being added 5. Plus 5, plus 5, plus 5, plus 5. So since the first differences are all the same, that tells me this is linear. It's not exponential, but it is linear, so that's good to know. All right, let's not try to break this anymore. So just like linear regression, just like quadratic regression, we're going to use exponential regression for exponential equations, for exponential models. It's going to work the exact same way. Does that look like it's like pulsating to you in a weird way? Like there's waves on the screen? Or is that just my screen? That was weird. I don't know if you guys can see that or not. But anyway, let's take this. Find an exponential model. So it tells us we're making an exponential equation right there. For the data, use the model to predict when the tuition at UT Austin will be $6,000. So we're going to go to our calculator. So let me close this. I'm just going to get rid of that. Pull up my calculator. Now this is weird because the x values here are like two things, right? I'm going to call, so it's 1999 to 2000. I'm going to call this year 0. 2000, 2001, I'll call that year 1. And then I'll call this year 2, year 3, and year 4. So I'm going to use those as x values. So we're going to go to stat. We're going to go to edit. We're going to clear these lists and type in this table instead. Clear that. And we're going to have 0, 1, 2, 3, 4. And then the dollar amounts, 3128, 3585, 3776, 3950, 4188. Okay. So I've typed it in. Now I need the equation. So we're going to go to stat. We're going to go to calc, and we're going to find exponential regression. Oops, I went too far. Let me try that again. Stat, calc, hit a wrong button. And I'm going to scroll down to find exponential regression. So there it is, the 10th one, exponential regression. Choosing that, we're going to go to calculate. And it gives us the equation. So look at the way it's written for us. And it's already on the screen here. So I'm going to go ahead and just pull that up. So our equation is y equals a times b to the x power. It says that there. And then it tells us that a is this number and b is this number. So we're going to plug those in. So it's y equals our a value, which is 3,235.64. And then our b value, which is 1.07. I guess that's good enough. And then to the x power. So there's your equation. All right. Now, it does ask us, though, we're going to answer this next. Predict when the tuition will be $6,000. Let me go and use a blank screen on this. So the tuition is $6,000. The tuition cost is my y value. So $6,000, it's giving me the y value. It's asking me to find out what year will be $6,000. So I know that my y value is $6,000, and I do not know what my x value is. So when I'm plugging the 6,000 into my equation, I'm plugging 6,000 in for y. Let me actually move this over a little bit so I get a little more space. 6,000 is where y equals. Then we have the 3235.64 times 1.07 to the x power. So we're going to solve this for x. Now, the first thing I'm going to do is, since this side's being multiplied by the 3,000 number, I'm going to divide that 3,000 number on both sides. Divide this by the 3,000 number as well. So let me pull my calculator up. We'll keep it there. Pull the calculator up. We're going to have 6,000 divided by that 3235.64. And we get 1.854. So that's 1.854 equals the 1.07 to the x power. So I have an exponential function. Remember, this is kind of annoying, but we did our exponential equations just recently. If I have the exponent like that, then what I have to do is I've got to go through the three-step process, put log on both sides, and work this problem out. So log on both sides, log of 1.854 equals the log of 1.07 to the x. We can move that exponent to the front now, so we have log 1.854 equals x times the log of 1.07. And since that's now in the front, I can divide both sides by that log 1.07 and cancel that out. So it's just x equals whatever this is, whatever log 1.854 divided by log 1.07 is. So let's go type that in our calculator. So log 1.854, parentheses, divided by log, I use right one, log of 1.07. Again, got to type that in correctly. Okay. And that is 9.12. So 9 years, because remember that x value is years. So it's saying 9 years essentially, right? So 9 years, if we look back at our table, so 4 was 2004, so that means 9 will end up being 2009. So the answer to this question is it will be on the 2008 to 2009 school year. That's when tuition will reach $6,000. Very interesting problem. Not too overly difficult if you did well on your test before, but you never know. All right, so use the exponential regression to find the function that models this data. When will the number of bacteria reach 2,000? So it's very similar to the last problem. So it gives us our x values of time and our y values of bacteria. So we're going to type this into our calculator. So our calculator, go back to stat, and let's edit these lists. So all I really got to do is add a 5 to this list. Let's put a 5 down there. And then I need to change all these. So let me just go ahead and clear all that. And type these in. So 200, etc. Okay, so let's get the equation, go to calc, and then we're going to choose exponential regression and hit calculate. So there's our equation. Again, that information is already written on the screen here. So let me just go back to that screen and work it out. So the equation is y equals, and our a value is 199.29, and then our b value is 1.25. That's to the x power. So that's our equation. Now we're going to use this equation to answer the question, when will the number of bacteria reach 2,000? So it's telling me the bacteria is 2,000. That's telling me a y value. So again, this 2,000 I'm going to plug in for y, and then I need to figure out what the x value is. What time will that happen? So if we plug the 2,000 in for y, then we're going to have 2,000 equal to 199.29 times 1.25 to the x power. So just like the last problem, since we're multiplying by that 199, I'm going to divide by that now. So cancel that out. So I need to do 2,000 divided by 199.29. So if you give me a second, I'm going to go ahead and just do that on my own calculator. So 2,000 divided by 199.29. And we get 10.0356. So 10.0356. And that's going to equal, since this is gone now, that's just equal to the 1.25 to the x power. So because our variable is in the exponent, we have to put log on both sides, just like the last problem. So if I put log on both sides, then this problem becomes log of 10.0356 equal to log of 1.25 to the x power. So just like the last problem, I'm going to take my x and move it to the front. So then we have the log of 10.0356 equal to x times the log of 1.25. And again, just like the last problem, because this is x times the log, I'm going to be able to divide by this log to cancel it out. But I got to divide this side by that same log. So divide this side by log 1.25 as well. All right, so that'll go away, and it'll be x equals whatever I get when I divide my two logs. So let me go back to my calculator. We'll keep that on the screen. We'll type in the log of 10.0356, close the parenthesis, and divide it by the log of 1.25. That is 10.33. So we'll just say 10. So it's the 10th minute, right? Because that is the x value, x in time. So it's 10.33 minutes. We'll just go ahead and say the 10th minute and have our answer be that. And I believe, so it says 10.3 minutes down here, approximately 10.3 minutes. We go to when it said 10 minutes, and that's fine. All right. I'm going to end this video here just because I feel like we've done enough examples for you to get the general idea. So let me know if you need anything. Give me a message on Remind. I'll see you guys later. All right. Bye.